Hello everyone, welcome back. So we will continue our discussion on flood frequency analysis. So I'm calling this part 2. I hope you watched the part 1 video. So in part 1 video what we did was we looked at how to calculate exceedance probability and return period for a given flow using a sample data. So in this slide I'm asking how do we get a flow corresponding to 2-year return period? So this Q2 here means a discharge corresponding to a 2-year return period. Then I'm also asking how do we find out the discharge value corresponding to a 50-year return period and a discharge value corresponding to a 100-year return period. So I'm showing you 3 samples for a site. I have used the same procedure that we have used in the previous video and in our assignment 18. So for flow of return period 2 or using the first sample, I get a value of 50,000 CFS. So I hope you are able to see this. If not, the flow corresponding to 2.07 year return period or approximately 2-year return period in this case is 50,000 CFS. For the next sample it is 46,200 and this sample is 53,000. And if you look at these return periods and probability values, I can actually use any of these. So I have a range of discharge values. So technically, if I want, I can take an average of these and these to get the answer for my 2-year return period flow. So each sample has 30 years of data, and finding a flow corresponding to a 2-year return period is easier in this case. So instead of just getting one value, I can take all these and take an average. Similar to that, if I just take this value, it's 50,000 here, it's 46,200 in another sample, it's 53,000 in another sample. But if I take an average of all these, the values are not as different as you see just for one single row. So with the 30 years of data, finding a 2-year return period flow is not that difficult. Now, what if I want to find a flow corresponding to 50-year return period or 100-year return period? And if you look at this column here for the return period for all these samples, you will see that we don't have any row that gives us return period of higher than 31 year. Okay, so this sample is inadequate for me to get a flow corresponding to a 50-year return period or 100-year return period. So to do that, I actually need data that is longer than 100 year, or most ideally it should be at least 200-year period of data if I want to get something reasonable for 100-year flow or for 50-year flow. So that's why using sample data is not enough for flood frequency analysis. Most of the times we are interested in design flows that are corresponding to return period of 50-year, 100-year, and in flood inundation mapping we also find out flows corresponding to 500-year return period. Now to get the flow for 500-year return period using this method, you need at least 1,000 years of data, which is not always possible. So this slide just makes that point that using the flood frequency analysis requires large sample. So instead of using sample, we think about the population or the parent distribution from which the data may be coming from. So if we can assume that the parent or population distribution for our data, then we can extract as many random values as possible. And this is where the probability density function comes into picture. Then the question is, how do we know what the parent probability distribution is for our data, or the probability distribution function for the population? If we know that, then we can extract as many values as we can, and we can create a large data set. So when we do this in practice, we actually don't extract all these random values. We use different ways to extract the information that we need. So the question that we want to first answer is, how do we know what the parent probability distribution looks like? To do that, we can actually use our sample and see how it looks. So here I'm showing you a frequency histogram that you can create from the sample data. And instead of explaining what this is, I can actually show you how I created this, and then from there we will go to the probability density function discussion. So what you see is the Excel data that I have. So in this column B you see the date, and in column C you see the flow values. So this is the annual maximum series for Wabash River. So you can actually create a histogram by using this time series. To create the histogram, what you can do is you can go to data, and then you should see the data analysis tool pack here. If you don't see that, you can actually go to file, options, and Excel add-ins and add this tool pack. So I'm going to go to data analysis, and then you will see lots of options here. And from these options, I'm going to select the histogram option and say OK. And then it will ask you the input range. So input range in this case is going to be our column C that has all the values. And the bin range, I'm just going to leave it blank and let the program pick for me. Then this one is asking, where do you want your output? I'm just going to say, give me the output in the new worksheet. And I'm also going to ask the program to give me all the plots after the corresponding to the histogram, and I say OK. And then, because I chose to have my result in a separate sheet, this is what Excel will create for me. So what you see in this, in column A, is the bin. So bin just means that the flow from 0 to 13,500, how many values I have. From 13,500 to 26,333, I have 4 number of data points. From 26,000 to 39,000, I have 24 data points. From 39,000 to 52,000, I have 23 data points, and so on. So if I wanted, I could have defined my own bin saying, give me the number of data points from 0 to 10,000, 10,000 to 20,000, and so on. But I just let the program pick it for me. And that is what is plotted in this frequency histogram. So in the first bin, I have 24 data points. In the second bin, again, I have 24 data points. And as the values in the bins get higher, you can see it is falling like this. So these are the number of data points in each bins, the column that you see here. And the orange line that you see here is basically accumulated values of those numbers in terms of percentage. So 100 means that this is accounting for all the data points. So this is what a frequency histogram is. On y-axis, you see the number of data points in each bin, and on an x-axis you will see the values for each bin. So even though you see one value here for each column, this basically means 52,000 basically means the range between 39,000 and 52,000, and same here. So number of data points between 52,000 and 64,800 and so on. So this gives you the actual frequency, which is the number of data points. You can actually convert that frequency into relative frequency. What you do is you just divide the number of values that you see here on y-axis by the total number of data points. So in our case, the total number of data points is close to 100. So all you see here is these numbers getting divided by 100, and this is what you see in the relative frequency plot. So once you see a relative frequency plot, you can think of this is for a discrete data set. Okay, so for a continuous data set, this may look something like this, or something like this. Okay, and then this becomes our probability distribution function, and I will talk more about this after we go back to our PowerPoint slide. So this is what we created in Excel. So as I said, you can actually convert this discrete plot into sort of a continuous function. So we usually don't convert this into a continuous function. What we try to do is we try to find a theoretical probability density function that will fit to our data and the properties of the sample. So each probability density function has some properties. So basically this is some sort of function, and we need to figure out which function fits our data. And there are certain properties of this function that we can manipulate, or the parameters of these functions that we can manipulate to fit that to our data. So you can think of this as fitting our discharge hydrograph that we got from HMS with the observed data. And when we were doing that, we were actually changing the parameters to fit those two hydrographs. So the two important parameters in fitting a probability density function are, the first one is location parameter, and the second one is scale parameter. So the location parameter defines where the location of this peak is, and the scale parameter basically defines how stretched the probability density function is. So I'm not going to go into all the details of how do you fit a probability density function to your data. That's like whole another sort of class. In this case, I just want you to know that you can actually fit a theoretical probability density function to your data. And to do that, you can actually use some of the properties of our sample, such as mean, standard deviation, skewness, to describe the nature of this probability density function. So the assumption that we are making here is that all the values that we have in our sample, they are coming from this theoretical probability density function. And if we are able to do that, then we can use the function itself to find the exceedance probability corresponding to a return period and vice versa, and the flow corresponding to the return period or the exceedance probability. Okay, so this is sort of fitting probability density function to your data 101. So this is very basic understanding of how this is done. There is a whole lot of methods and procedures that you can do to fit your data to a probability density function. So for now, I think this discussion is enough for you to understand what we are trying to do. As I mentioned, we will use some of the statistics from our sample to fit the PDF to our data. And what I'm giving you here on this slide are expression to get the sample mean, sample standard deviation, and coefficient of skewness. And I'll just explain in a while what skewness means. So you should be able to to find the location and scale parameter for many distribution by using these three properties. So I mentioned coefficient of skewness in the previous slide. Coefficient of skewness basically defines or describes how skewed your distribution is. So normal distribution, you can see it's perfectly symmetric, so the coefficient of skewness is 0. When the distribution is negatively skewed, you can see the peak is to the right. When the distribution is positively skewed, which means the coefficient of skewness greater than 0, the peak is on the left hand side. Okay, so this is positively skewed, this is negatively skewed, and this is perfectly normal. And if we go back and look at the distribution that we got from our data, you can see this is positively skewed. Okay, so once we know all this, now let's see how we can get the flow corresponding to a return period if we know the distribution function. So what I'm showing you on this slide are probability density function for a normal distribution and cumulative density function for the same distribution. Okay, so usually this is described by some expression fx. So cumulative density function is basically integral of this normal PDF. Again, these are just accumulation of all the values that you see on normal PDF here, and that's why this value is 1. Okay, now when we think of a discrete, so if you remember when I discussed probability and statistics in my first video, I gave you an example of deck of cards. So the probability associated with any single experiment with deck of card is a discrete probability because you have only 52 outcomes when you use that. So when you have a discrete probability such as that, you can use a probability density function and find out probability corresponding to any outcome. Okay, so this is true with discrete probabilities. That's why the expression that you see here is probability that a random variable x will take this small value of x can be given by a point on this probability density function. When you have continuous probability similar to what you have or what we have with stream flow, it is almost the probability that you can get an exact value on this function is close to 0. So instead of getting an exact value, what we try to do is we try to get the value in a very small range and then find the probability associated with it. So this is how you can use a probability density function to get the probability for a continuous function or continuous random variable. A better way to do that is use a cumulative density function instead of a normal probability density function. With cumulative density function, if you find a value at any location along this curve, that value gives you the probability that a random variable will take a value less than this. So basically you are getting the area under the curve for this point, and the value of that function at this point will give you probability that the random variable x is less than or equal to some values, this small x. Now this will look familiar to you, probability that x is smaller or equal to this x, because when we described or defined exceedance probability, this is the expression that we used, probability that x is greater than or equal to some value, the small x. So if fx gives us this, which is p greater or p of x less than or equal to small x, then 1 minus x should give us the opposite. So remember, with probability theory, if the probability of success is p, the probability of failure is 1 minus p. So with the same logic, if fx is equal to p of x less than this x, then 1 minus fx will give me p of x greater than or equal to x. So if this is true, then we can, instead of probability, we can just say our exceedance probability is 1 minus fx. Exceedance probability can be written as 1 over return period, and then we can rearrange this. And what you see here in this last expression is that, so we can think of x as our discharge and t as the return period. So for any return period, we can find the expression for q if we can get the inverse of our cumulative density function, and I will show you how to do that. So this is how we can use the cumulative density function to find discharge corresponding to any return period. Now all this will look little theoretical to you, but we will see how can this be done once we know what f is for different probability density functions, or cumulative density functions in this case. So these are some of the probability distribution functions or models that are used in literature. So normal is this. Log normal is a skewed distribution, exponential gamma. So we don't have time to cover all these probability density functions, and if you have taken class in statistics, some of you be more familiar with this. In this video, we are going to focus on two probability density functions. The first one is the extreme value type 1 or EV1, and the second one is Log Pearson Type III. And Log Pearson Type III is actually a method that is recommended by Bulletin 17B. So Bulletin 17B is just a guideline document created by the United States Geological Survey to perform flood frequency analysis in the US, and it is actually used a lot in other parts of the world. So let's see how we can perform flood frequency analysis by using these two methods, EV1 and Log Pearson Type III. So what you see on this slide is the expression for the probability density function for EV1, and this is the cumulative density function. So on this picture, you just see the probability density function. The CDF corresponding to that will look something like this. So this will be 1.0, and the expression for this CDF is given by this. And these plots that you see here, they are plotted by using this expression, by just using different values for the scale and location parameter. Okay, so you can see these two, the scale parameter is the same, the location parameter is different. So in the first one, lambda is equal to 0.5, in the second one lambda is equal to 1. So location parameter basically just shifts the peak of this distribution, and the scale parameter stretches. So you can, this has a different scale parameter, this has a different scale parameter, and this has a different scale parameter. Okay, so again, location parameter is related to the mean, and the scale parameter is located to the standard deviation. And again, this is sort of self-explanatory. So when you change the mean, this gets shifted, and when you change the standard deviation or the variance, you can see there is more scatter in the data and the distribution gets stretched. Okay, So again, the question is, now that if you are going to use EV1 distribution, how do we get flow corresponding to a certain return period? So let's see how we can do that. Now let's say I'm interested in a flow corresponding to a certain return period, which is t. So this is the expression that we have for the cumulative density function, so fx. So for exceedance probability, we will use 1 minus fx, and ep is exceedance probability. So instead of exceedance probability, I'm using this as 1 minus 1 over t. So what I have done here is I have replaced this part with 1 minus 1 over t, and then I solve for x. And when you do that, you end up with this expression, or this to be specific. Okay. So what this expression says is that xt in this case is basically flow corresponding to t return period. So if you're performing flood frequency analysis using EV1 distribution, all you need to know is the sample mean, the sample standard deviation, and the return period for which you want to get the discharge. Once you have that, this will give you the discharge corresponding to T. Okay. So one good thing about EV1 distribution is that it is invertible. So what I mean by that is I was able to simplify this expression to get an expression for xt. So that's why it is invertible. But some functions are not invertible, which is one of them is Log Pearson or Pearson Type III. So this is the expression for density function for Pearson Type III. So this is the gamma function, and this actually has 3 parameters. Okay, so lambda, beta, and this epsilon. So this is Pearson Type III, and the distribution that we use is Log Pearson Type III. What that means is that if y is equal to log x, and if y follows Pearson Type III, then x follows Log Pearson Type III distribution, and that's again the same expression that we saw in the previous slide, but instead of x, now we have y here, but y is log of x. So in all these slides I'm using x, but just read that x as q. Okay, so that's what we are interested in. We are just using x as our random variable, but the variable that we are interested in is q, which is the discharge. Okay, so the question is, EV1 is invertible, so we were able to get an expression for x, but Log Pearson Type III is not invertible. So in that case, we have to use a different technique. You cannot easily expand that expression that we have for the density function. So instead, what we use is we use the method called frequency factor method. So the frequency factor method gives us this expression. So this is again our discharge corresponding to a certain return period. This is our sample mean. This is our sample standard deviation. All we have to do is find out this kt. So k is the frequency factor corresponding to a t-year return period. Okay. The question then is, how do we find kt? Okay. With EV1 distribution, because it is invertible, we can just use the expression that we had before to come up with an expression for kt. So if we are using EV1 distribution, this is the expression for kt. Once you know what kt is, then you can just put that in this expression and get xt. xt again, just read this as qt. So x bar is the sample mean, and sx is the sample standard deviation. Okay. So with EV1 distribution, you can either use the frequency factor method or you can use the expression that we derived before, which is basically this, to get xt. Now let's see how we do that using the Log Pearson Type III distribution. So in Log Pearson Type III distribution, usually we start with our sample. So in this case, we have a discharge annual maximum series. Then from that, we create a y series. So y will be log x. So again, read that as log q. And then we find the sample mean and sample standard deviation of this y series. Okay. Once we know that, then we can find yt, which will be y bar plus kt times sy. So y bar is again the sample mean of y series. So y in this case is log of q, and sy is standard deviation of y series. So y series is created using q, so it is easy to find y bar and sy. The question again is, how do we get the frequency factor kt, and then we can use this expression to get our xt. So xt will be 10 to the power of yt. The question still remains, how do we get kt? Now there are multiple ways to get kt. You can find expression for kt using Log Pearson Type III, but in this class we are going to use this table 12.3.1 in Chow Maidment Maze to get kt, and I will show you how you get that. The only thing you need to know to get kt is t, which is return period, and your coefficient of skewness, which will be for the y series. Okay. So this is the table 12.3.1 in the book. So the idea here is, if you know the coefficient of skewness and if you know the return period, then you can get the frequency factor. So let's say I'm interested in return period of 50 years and my coefficient of skewness is minus 1.6, and then this will be the frequency factor for. So I use this and go back in this expression here, put that kt, get my yt and the xt, which will be again read xt as qt, and then I can get the final answer that I'm interested in, which is the discharge corresponding to a return period of t. Now some of this may be little vague for you still. We will clarify and sort this out when we will do our next assignment. So look out for that video, and by following the assignment you should be able to know how we can do flood frequency analysis using EV1 distribution and Log Pearson Type III distribution. So with that, I'll stop here, and if you have any questions, feel free to email me. Thank you and bye.